welcome to the YouTube channel for Wayne State University's chapter of the Tau Beta Pi Engineering Honor Society. My name is Austin Heitzman. Today in this video we will be looking at Chapter 1, Section 3 of the Linear Algebra course. If you have seen the past couple videos we've done for this, with sections 1 and 2, we have looked at systems of equations and basically translating that information into a matrix. But today we are going to be looking at a little bit differently. So far we have basically just done row operations within a matrix, but as you can see here, with certain restrictions, and this is something to really highlight, we'll be talking about this, you can actually perform algebra between two or more matrices, right? So just for example, say we have matrices like A and B, you can, with certain restrictions, you can say A plus B, and you could say A times B, and you could also say some number C, just a real number, times A, right? So you can add two matrices together, you can, in some situations, multiply them, and you can also take a scalar, a real number, and multiply that to an entire matrix, right? Notice there are a couple exclusions here, right? Now we aren't looking at subtraction on this list, but we do have scalar multiplication and we have addition. So we could also say A plus negative B is essentially a subtraction. So subtraction is sort of within the purview, we just have to look at it a certain way. But we are not going to be seeing any division. No, we do not divide matrices, right? So that is kind of a relief. I don't know about you guys, but division is usually the hardest of the bunch. So we're basically going to be looking at some pretty standard operations. Like I said though, certain restrictions. So let us dive in. Addition, probably one of the easier ones of these. Basically, it's just done via components, right? So if you have a matrix A, let's say this equals just 0, 1, 2, 3, and you have a matrix B of the same size, 3, 4, 5, 6, then A plus B is basically going to be the addition of each individual component going exactly where it is on these matrices, right? So we have a 0 plus 3. It's going to mean that A plus B in this cell is going to be 3. We have a 1 plus 4 is 5. 2 plus 5 being 7. And 3 plus 6 being 9, right? So super simple. There's nothing any like crazy complicated rules here in terms of the actual process itself. Basically just add the components together. Components being each of these individual cells, right? Now, I was very particular with these matrices that I chose for this example. You notice that they are the exact same size, right? So A is 2 by 2 and B is 2 by 2. That is a restriction. So in order to add two matrices, they must be the same size. Now they don't need to be like square matrices, right? So we can have a 3 by 2 plus a 3 by 2. That's fine. You can have like a 26 by 100 plus a 26 by 100. That's all fine. But 3 by 2 plus a 2 by 3 is a no. We don't want that. And basically when you stop to think about that, like, that kind of makes sense, right? I mean, if A is going to look something like 2, 3, 4, 5, 6, like a 2 by 3 matrix. Remember, we're doing rows and columns, so 2 rows, 3 columns. And B is going to be a 3 by 2 matrix. Well, if we're going by components, and we need to put each component exactly where it goes in the solution, right? How are we going to add these together? Like what would the size even be, right? You know, there's nowhere to put this 3. There's nothing to add this 3 to, for example. So this just doesn't work. So that should make it a little bit simpler to remember. Basically, just add the components together individually, and the 2 matrices must be the exact same size. Properties of matrix addition are as follows. So by properties, we're kind of saying like, you know, like what works and what doesn't, right? In a very general case. So if you have matrices say A, B, and C that are all m by n, and remember that's just like a very general way of saying the size of the matrix. We can say that addition, just like it is with real numbers, is associative, which means that A plus, I'm going to group together B and C here. That's going to be the same thing as saying if I group together A plus B and have C on the outside, right? So that's one property of addition. You can also say that this is commutative. So A plus B is the same thing as saying B plus A. Now if we also have a real number, say we introduce a real number called C, we already have a matrix C, and that might get a little confusing. So I am going to call this Z, because it sounds like C, why not? Is a real number. Then we can also say that matrix addition is distributive, right? So if you'll remember that from early algebra, we're going to say Z times, in parentheses, A plus B. It's going to be the same thing as saying AZ plus BZ. Right, and pretty much all of the properties of addition for matrices will pretty much boil down to these. It's associative, so grouping does not matter. It's commutative, so order does not matter. And it's distributive, so if you have a real number, then multiplied by an addition within parentheses, you can apply that real number to both of the addition components individually. So from here, we can look at scalar multiplication, and this is going to be really pretty simple. I'm not going to spend too much time on it because just like we did addition component-wise, we're going to do scalar multiplication component-wise as well. So say we have a matrix A and a number, we'll stick with Z. Just going to sketch out a random matrix here. Size in this case does not matter. We will say that A is a 2 by 2 matrix made of 0, 1, 2, and 3, and Z is the number 2, well, A times Z, or you'll often see it as like ZA, right, is just going to be Z applied to each component of A, Z multiplied by each component of A, right? So 2 times 0 is 0, well, 2 times 1 is 2, there's the 2. 2 times 2 is 4, and 2 times 3 is 6. And that's all we're doing with this, right? So there's not going to be any like crazy restrictions since we're not dealing with 2 different matrices. We don't need to worry about their size lining up or anything like that. Just basically plug the multiplication of the scalar into each component. Now, glad we got the easy stuff out of the way to build our confidence, because multiplication does get a little bit trickier. So for matrix multiplication, we need to introduce the concept of a dot product. So the dot product can be a little bit tricky to explain, and I feel like the easiest way is probably to just give an example. If you've ever studied physics, this is probably pretty familiar to you in terms of taking the dot product of 2 vectors, but if not, that's okay. We're going to try to go through it now. So as an example, I am just going to give 2 vectors. Let's say we have a vector v. Remember, a vector is very similar to a matrix. It's just going to have the one column, right? So if I have a vector v, and I'm just going to give it 2 components, just 1 and 2, just to keep it really simple. And say I have another vector called w. We'll also give this one 2 components. Got to be the same size. Then, so a vector v is going to be 1, 2. Vector w is going to be 3, 4. If I want to take v dot w, that's going to be the notation that we use. It's not going to be standard multiplication. I know sometimes for multiplication we'll use a dot to signify that, but this is a little bit different. V dot w, we are basically going to multiply the adjoining components and then add it together. So the result is just going to be a single number, all right? So in practice, what this looks like for v and w, it would be 1 times 3 plus 2 times 4. So I just took 1 times 3 because that's both the first components, and then 2 times 4, which is both the second components. And that's going to equal 3 plus 8, which is 11. So that 11 is my answer to this, right? Note that the result is a scalar, a non-vector number. All right, so how does this apply to matrices? Well, basically what we're doing is we're going to take 2 matrices, A and B, and we take the dot product of A's row dot B's column, right? This is going to take just a lot of rote practice, basically. But I can sketch out like the general formula as this. So for 2 m by n matrices, actually, I apologize. So we're going to get into those restrictions for just a second, because they are a little bit more complicated, but in terms of a general form, we can let A be an m by n matrix and B be an n by p matrix. So their product, multiplying these 2 together, is going to be an m by p matrix. where the components are calculated, and again, we're just going to make this a general form. So we can write this as AB, the ijth component of AB, right? It's going to be A, I1, B1J, because we're taking the row, the ith row, dot product, the jth column, plus A, I2, B2J, plus however many rows and columns you have. And then the last is going to be AIN, BNJ. If you remember summation notation from calculus, you'll recognize that we can write this as the sum from k equals 1 to n of A, I, K, B, K, J. That looks like a mess. I recognize that this looks like a mess. I promise, as soon as you start just plugging away and practicing, and we will do some examples, this is going to make a lot more sense. But as you can see, there are some restrictions here to what can be actually multiplied. And if you'll notice when I set up this generalization, A needs to be m by n and B needs to be n by p, whereas AB is m by p, right? So basically the number A's columns needs to equal the number of B's rows, right? And a kind of handy way to remember this, when you're doing these problems and you're kind of analyzing, like, let's say A is 3 by 2 and B is 2 by 3 matrix. Well, if you kind of position this so that if you can have a line connecting A's columns and B's rows, just for your own visual understanding, I see that these two numbers are the same, so we can multiply these, and the result is going to be given by the numbers left over. So in this case, we can check that the number of A's columns is 2, the number of B's rows is 2, we can multiply these, and the result, A times B, is going to be a 3 by 3 matrix, right? So that's kind of an interesting little trick to remember. And now in terms of properties, really quick, so multiplying A and B is associative. So A times B times C, with all of those being some matrices, is going to be the same thing as grouping A and B together and multiplying them by C. But this is not commutative. Not inherently. There are some matrices that can commute, but in general, it is not true to say that AB equals BA. Not true. No. It is, however, distributive. Which means if I have matrix A times matrices B plus C, it's going to be the same thing as saying AB plus AC, assuming that A, B, and C meet these restrictions that we just talked about. Alright, so I know that's kind of a lot, but there is just one more thing we need to talk about before we dive into actually putting this into practice, and that is going to be the idea of transposition. Thankfully, this is quite a bit easier than the multiplication that we just looked at. Basically, the definition, so if we have A being an M by N matrix, then the transpose of A, or A transpose, which is usually marked with this notation, like A with a superscript of T, is an N by M matrix, where the ijth term of A transpose is equal to the jith term of A, right? That's a very complicated way of just saying that the rows of A turn into the columns of A transpose, and vice versa. So this is not very hard. This is something that can usually be done pretty quickly. There are a few different properties to this, and I basically already explained the process, but just to give it like a really solid idea, I'm just going to give a really quick example. Let's say I have a 2 by 3 matrix. I'm going to plug 0, 1, 2, 3, 4, 5, just make it really simple. If we call this A, then A transpose is going to be a 3 by 2 matrix. So this row right here is going to become the column of A transpose. Likewise, this row right here is going to be column. So the first row becomes the first column, the second row becomes the second column, so on and so forth for however big of a matrix you have. The properties of transposition are as follows. If, I should say, 4 matrices A, B, and C, I can say that if we put A plus B in parentheses and a transposition outside of it, it's the same thing as saying A transpose plus B transpose. Similarly, same with multiplication. So if we put A and C in parentheses with the transpose outside of it, it's going to be a little bit different this time. I want you to notice a little bit of a difference is that the result is not going to be A transpose times T transpose, but the opposite is going to be C transpose times A transpose. So that's going to flip. Now, since A transpose is basically just a little sort of like inversion trickery of A, an interesting fact about this is that if you take the transpose of A transpose, that's just going to put you right back at A, right? And finally, if Z is a scalar, putting Z times A in parentheses and transposing that is going to be the same thing as taking those parentheses out, just doing the transpose of ZA. And similar to transposition, kind of going off of that idea, is the idea of a symmetric matrix. So far this hasn't been quite as common as transposition or matrix algebra, but it's worth mentioning. So the definition of this is that matrix A is an n by n matrix. It's a square matrix. The number of rows equals the number of columns. And symmetric if A transpose is equal to A, right? So the matrix is going to be the exact same thing if we replace the if we replace the contents of the rows with the columns, if we swap them out, right? And the main restriction on symmetricity is just that the matrix must be a square matrix. The number of rows needs to be equal to the number of columns. We usually call that n by n. Alright, this has been a lot of word at you, so let's try to incorporate some numbers. I drew up this really quick example from the textbook, and it should give enough variety to kind of give you an idea, but like I said, the main way to teach yourself this is just have at it and do as many of these as possible. So let's start by analyzing this. So the first one, we're going to have matrices A, B, and C as outlined in the problem. And part A asks us to find the result of taking 2A transpose minus B transpose, right? So the way I like doing this is to just start by writing them all out. In fact, I'm not even going to start with 2A transpose. I'm going to start with A transpose. Remember, a transposition, we're just taking the rows of the original and turning them into the columns of the transposition. So if the first row of A is 2, 0, negative 1, then the first column of A transpose is going to be 2, 0, negative 1. Similarly, the second row of A is 1, 0, negative 2. So that is going to become the column of A transpose. Now it's asking for 2A transpose, right? And we said scalar multiplication is just going to take each individual component and multiply it by the scalar. So 2 times 2 is 4. Anything by 0 is 0. 2 times negative 1 is negative 2. And so on. And then, now we also have a minus B transpose, right? So that's the same thing as saying plus negative B transpose, right? So you can do that in whichever way makes more mental sense to you. I find it a little bit easier to write it out as a negative B transpose. And I trust that that's not too many steps taken at once. But to accomplish this, we're going to take B. I am going to do these 2 steps at the same time. So I am going to transpose B, and I'm also going to flip the signs, right? So negative B transpose, according to B, is going to be 3, negative 1, negative 1 going down. And then the second column is going to be the negative of the second row. So 3, 3, 2. Now these 2 things here are what I need to worry about, right? We are doing addition, so we need to make sure that they are the exact same size. 2A transpose is a 3 by 2 matrix. Negative B transpose is a 3 by 2 matrix, so we are good to roll. The result then, if you haven't guessed, is, let me write this out clearly. Just adding each individual component. Since we already boiled that negative into when we made negative B transpose, we're just going to have to add it at this point. So 4 plus 3 is 7. Going across the rows this time, we have 2 plus 3 is 5. 0 plus negative 1, negative 1. 0 plus 3 is 3. -2 plus -1, -3, and -4 plus 2 is -2. And that is our answer. Woot woot. 1 down. Now, the second one looks very similar to what we just did. It's going to be B transpose minus 2A. We're not going to transpose the A this time. So, just draw like a green line to separate these guys. I can write out B transpose. No need to negate it this time, so it's just going to be first row of B becoming the first column of B transpose. Likewise with the second. And then we have a -2A. But what we can notice, I don't even need to do any -2ing, right? Because A is going to be a 2×3 matrix, whereas B transpose is a 3×2 matrix. And what do we know about addition, subtraction of matrices? They need to be the exact same size, right? So this is actually not possible. Dimensions are different. You can work out what -2A is just for practice, but I am a fan of not doing more work than I need to when I notice that that's the case. So let's just move on to the last one. The last one, we have A transpose times C, all of that times B. So let us work one by one. A transpose. We are once again making the first row of A the first column of A transpose, the second row of A the second column of A transpose. We already have C right here, so let's see if we can do this. I'm a fan, especially with multiplication, of like actually writing out both matrices side by side because it makes the multiplication a little bit easier. So that's what I'm going to do right now. And we can take a look at this for just a second. We have a 3×2 matrix is A transpose, and a 2×2 matrix is C, right? The columns of A transpose equal the number of rows in C. So we are good to go. And our result is going to be a 3×2 matrix, right? Just a good little practice thing to keep in mind as you're working. So, I'm going to do this down here so we can all keep this in sight. And I'm going to do this kind of drawn out so that you can see like really what I'm doing. Professors will often go very quickly through this very soon after you learn it. So just try to keep it slow if you need to, and just do a bunch of practice. So we're going to take the dot product of the first row of A transpose and the first column of C, right? So that is going to be 2 times 3 plus 1 times -1. And that dot product is going to be this entry of the matrix, right? I'm going to need to scroll over here because we're going to need some room, but that's okay. I'm going to write it out all as the formula, and then we'll actually go in and solve it, right? So likewise, for the next entry, we have the first row of A transpose dot product with the second column of C. So that's going to give us 2 times -1 plus 1 times -3. All right, the second is going to be very easy because it's just going to be all zeros, but we'll still draw it out so everybody's on the same page. This next cell is going to be 0 times 3 plus 0 times -1. And then same deal for the second column of C, 0 times -1 plus 0 times -3, right? And you'll see how this is stacking up to be a 3 by 2 matrix, excuse me. All right, final row of A transpose with both columns of C. That's going to give us -1 times 3 plus -2 times -1. And finally, -1 times -1 plus -2 times -3. All right, this looks like a mess, but as soon as we do these dot products, we're going to see that it just looks like a normal matrix. So, first cell, 3 times 2 is 6, plus -1 is going to be 5. 2 times -1 is -2, plus 1 times -3, that's going to be a -2 minus 3, going to give us a -5. And you'll notice that second row of A transpose is both zeros. All of this is going to come out to be 0, and you can do those dot products if you don't believe me. But for the last row, we are going to have a -1 times 3, so a -3, plus -2 times -1, which is a +2, so that's going to be a -1. And finally, -1 times -1 is 1. -2 times -3, 6. So we have a 7 here. Normal matrix. See what I mean? So that is pretty much what we're dealing with. You're going to have a chance to do a lot of these, and you're probably going to need it just to get the rhythm down. So my suggestion is to just keep plugging away at it, keep trying, and always ask for help if you need it. Thank you so much for watching this. I hope it did clear up some things, kind of give you at least a basic overview before or after class. And be sure to check out the rest of our channel if you need any other tutoring for pretty much any STEM class. We have plenty of like science, math, engineering tutoring videos on our channel, with hopefully more to come. I will see you next time with an introduction to the inverse of square matrices. But until then, I hope you enjoy yourself. Have a good day.